Okay, so last time we talked about the difficulties in dose selection or dose response studies in clinical trial. It's mainly because for clinical studies, if you want to study an individual dose, you have to allocate some patients into it. And so if you want to study many doses, the investment is pretty huge because you have to have a huge sample size in each treatment group. And this is a case where we're very lucky with very few subjects per dose, we're able to see some kind of trend. But in most cases, we're not going to see things as pretty as this. It's going to be a lot of distribution around here, a lot of distribution around here, a lot of distributions. And then you simply plot the means or medians, it have some kind of upward trend. That's pretty much what we can do about. All right, let's see. Okay, so we talked about drug label before. We talked about the development planning before. All right. Now, in those findings, when design a dose finding study, what are the issues we should consider? Of course, we cannot do individual dose response. We have to look at the global dose response from the clinical trial setting. And what is our objective? What does the label say? How many doses we want to deliver to the market, and what range of doses we're going to study, right? How many doses to be tested? So when you design this trial, you need to know the number of doses and what are your endpoints, what you're trying to measure. I will talk about exploration and confirmation again. I mean, we talked about this before. The POC is confirmation because that's a go no go decision. But dose ranging is an exploration practice. So we want to explore a range of different doses and see if we can find any doses that's efficacious. All right, in most of drugs, we need to recommend a few fixed doses. But if you have a very wide therapeutic index or therapeutic window, it is possible to use just a single dose. Concentration response, we're not doing much of that nowadays. We're mainly focused on dose response. For concentration response is that instead of looking at the doses the patients are being delivered, they're looking at the PK, the concentration, and then look at that concentration relating to a response. So we don't do that. It's too much difficulties once you market the drug. So we look at PK/PD before. And dosing frequency. When determining dosing frequency, the pharmacodynamics of a compound should be considered as critical as pharmacokinetics. So in contrast to the PK half-life, the PD half-life could be dose dependent. And we need a control release formulation and all these kind of issues. All right, we looked at this before. All right, so let's get into dose response. So what do you see in this picture? So I got a study with low dose, medium dose, and high dose. So I typically, when I present this slide, I say, do you see a dose response? And most of the audience say, well, it looks like there's a dose response, but 19, what's your trick? So here's the problem. This design is without placebo. Placebo control is absolutely important. It's very critical, all right? So whether you have dose response or not, it doesn't matter. The drug doesn't work. Okay, so that's sort of good enough to say, let's stop developing this drug. Now, what about this case? All right, so we have an active control here. We have an active control here. And we have placebo here. And it is clearly that the test drug does not work. All right. So again, when I present this to the audience who are most drug developers, I would see their response would be kind of disappointed. I say, look at these results. How do you feel? I mean, the general feeling is disappointed because the drug doesn't work. All right. And I say here is that this is a very successful study. We use one study to fail an unsuccessful drug. All right. So again, the way to evaluate the study should be independent of the way to evaluate the drug. So the drug failed. That doesn't mean the team does not do a good job. This is a very successful study. You use one study to deliver a very clear decision. So the team did a good job in designing this trial, in conducting this trial, so that upper management can make a clear decision. All right. So what would be a case of a failed study? Let's look at this. Okay. So you cannot differentiate active control from placebo. There's something wrong going on here. All right. There are two possibilities. One possibility being the placebo response was too high. All right. So the drug really works, but the placebo response just happened to be too high. The other possibility would be the active control response was too low. We know the active control has already been approved, already on the market and all that, so it should be better than placebo. But if we cannot differentiate active control from placebo, we don't know whether the study itself is valid or not. All right. Of course, there's many other potential explanations, but this is a failed study because we cannot tell whether the drug works or not. Active control is not strictly necessary in phase 2. It serves as a useful control in case the drug doesn't work or works poorly. So if your test drug doesn't work, so at this point in time, you want to compare active control with placebo. All right. A negative comparator may also be critical if there's an effective competitor on the market. And then, so you may want to consider at the phase 2 to make some comparisons. But again, this comparison, you cannot clearly define a non-inferiority or superiority kind of things. It's mainly for exploratory purposes. This is a very important example here that in the earlier stage of my career, I was working on this drug, and for this endpoint, it is lower means better, okay? Like lower blood pressure or lower pain or things like that. So lower is better. So in this case, so the first study, so I call it drug A, all right? So the first study in drug A, I would say the first dose ranging study, we have placebo 80, 120, 160, all right? So you look at these results. So what can you conclude about this study, all right? Now, everybody can agree the test drug worked. There's a clear differentiation between placebo and any of the test doses, okay? Now, the next thing you're going to say is that maybe 80 milligram is too high because you don't see a dose-response relationship. You would anticipate the dose-response relationship, but 80 tend to be high, so you don't get to see the dose-response relationship. All right, so we did next study, so I call it study 2, okay? So study 2, we used 40, 80, and 120. All right. So again, 40 works, but we did not see a dose-response relationship. But apparently 120 is doing pretty good. You look at this, and you look at this, you say, so 120 is pretty good. So we engaged in phase 3 study. So after study 2, we started the phase 3 study with 120 milligram, all right? And of course, in this process, we have an end of phase 2 meeting with FDA. And FDA questions about the dose. So we designed a third study. So the third dose finding study, we used 2.5, 10, and 40. So remember we started with we started 160, right? 80, 120, 160, and then we went down to 40, 80, 120. Now we go down to 2.5, 10, and 40. And here's the results. All right, so we see a dose response here. All right, now what's the problem with this set of studies? Okay, so we have to redesign phase 3 studies with 20 milligram, 40 milligram. That'll be the appropriate dosage for phase 3. It took us 3 studies to find the efficacy dose response. And the large scale study was 120 milligram, cannot be used for registration. Filing was delayed by many years. This is a huge failure in dose finding, in dose ranging. All right. So we used 3 dose ranging studies to find the right range of doses. And our phase 3 study used 120 milligram, cannot be used, and it's a major erosion into the patent life. So what is the problem with this set of studies? All right, the fundamental issue is as follows. Okay, if I'm designing a first dose ranging trial for this new drug, for this test drug, and I'm making 2 key assumptions. Okay, the first assumption is I get my MTD correctly. All right, so last time I mentioned sometimes MTD could be overestimated, sometimes MTD could be underestimated, but in this case I'm assuming MTD was estimated correctly. All right, so it's a good guess. That's my first assumption. My second assumption is monotonicity. So as dose increases, efficacy increases. As dose increases, efficacy increases. So given these 2 assumptions, I have infinite number of possible dose response curves, right? So now if you decide to have a dose ranging trial with 3 doses plus placebo, how are you going to allocate it? So of course, if I know it's curve number 3, I'm going to allocate the high dose here, the medium dose here, the low dose here. All right, if I know that's curve 3. Or if I know it's curve 2, I'm going to allocate high dose here, medium dose here, low dose here, right? Now, if I know if it's curve 1, I'm going to allocate high dose here, medium dose here, low dose here, right? But the question is, I don't know which curve it is. All right, I got a very good, sort of a very high MTD. Suppose this is 1,000 milligram. I got 1 gram I can play with. And the question is that the activity could be between 0.0001 milligram and 0.001 milligram or something like that. Or it could be between 100 milligram, 1,000 milligram, that I have no idea. But I'm given 3 doses, how I'm going to allocate. Then, of course, people will say, why do you want to limit the 3 doses? Can you do 4 doses or 5 doses or something like that? And of course, the natural question is how many doses will be sufficient. All right. And the question is still there, even though you can allow for 10 doses. If your dose response curve is curve 1, you'll allocate all 10 doses here. You're not going to find the dose response. All right, if your lowest dose is starting from here. All right. So I think that's the biggest question concern in designing the first dose ranging trial. So multiple arm dose response trial, monotonic dose response relationship is very common in practice. So the only major therapeutic area where dose response or monotonicity you didn't see monotonicity is CNS, central nervous system drugs like anti-anxiety, antidepressant, or anti-schizophrenia. So many of these CNS drugs, you may not have monotonic dose-response relationship. But for most other type of drugs, monotonic dose-response relationship is very common. And of course, you have two treatment groups are not sufficient to characterize the nonlinear nature of the dose response. Two groups, you're going to have MTD plus placebo. That's a POC. That's not a dose ranging. All right. So multiple arm trials, especially informative for drugs with wide therapeutic window. So you want to allocate more than 2 or 3 or 4 doses. Okay. All right. The key question is what range of doses should we consider? All right. Ideally, you want to do this in early phase 2 because you don't have much information available. All you know are preclinical data, you know the PK data, you know MTD, and we're assuming all this knowledge and information are correct. And we know 0, and we know that's placebo, and we're assuming that we know the MTD. And we need to explore an adequate dose range and selecting doses for early dose ranging studies. So how are you going to select these doses? All right. Now, we want to examine a wide range of dose in early development and follow the study with a narrower dose range. So that was my thinking back in the 90s or early 2000, that you start with a dose ranging trial with a wide range and use pharmacological response or biological markers from animal studies and phase 1 studies to guide the selection of the dose range in the early studies. All right. And then if you can be very ambitious, although not always attainable in early studies, a goal should be try and define the MTD, the maximally effective dose, and minimum effective dose. That's very ambitious goal. All right. So how many doses do we test? So we're now in phase 2 dose ranging. We want to try a few doses. So can you set up all possible doses? No way. All right. I mean, there's infinite number of doses because you're looking at the continuous curve, right? But you can only study a limited discrete dose formulations. All right. Do we include control groups? Of course, from the example I showed you earlier, we need to have a placebo control. All right. So placebo control. Sometimes you have active control. The main problem is really the dose spacing problem. All right. Now I want to spend some time talking about just the thinking or the understanding about the dose spacing. All right. In animal studies, it's very typical. People are going to do like, well, they're doing like milligram per kilogram. They can do 0.01 and 0.03, then 0.1, then 0.3, 1, 3, 10, 100, 300, 1,000, and so on and so forth. All right. Now, that way of thinking is very consistent to the human mind of thinking. All right. You're looking at a sort of a log scale, right? 0.01, 0.03, 0.1, 0.3, and so on and so forth. Or people can suggest like we can use Fibonacci series. Fibonacci series is like 1, 2, 3, 5, 8, 13, 21, that kind of stuff. In other words, the third number is the sum of the 2 prior numbers, right? 1, 2, 3, 5, 8, 13, 21, so on and so forth. That's Fibonacci series. Or you can use modified Fibonacci series. In other words, you want to have a wide range of doses so that your spacing would be reasonable. All right. Now that's how we think, because we think from lower number up to upper number. But in fact, for dose ranging design, you're starting from the high point from MTD to move down. All right. So, well, you can say from MTD moving down, that's okay. We can do like, we start with 1,000, we go down to 500, go to 250, 125, and so on and so forth. That's fine. That's log scale, right? So how can we sort of communicate with the team so that the team can understand that really about the dose ranging is not how high can you go, because your upper end is limited by MTD. If you want to have a wide range, it's how low can you go. All right. So remember, the dose range of a given design is defined by the highest dose divided by the lowest dose. All right. So if I start with 100 as my MTD, all right, I can do, of course, 100, 80, 60, 40, 20. So that's one kind of dose spacing. All right. Or I can do 160 and 20. All right. If 160 and 20, I got a dose range of 5, right? Or I can do 150, 25, 12.5. Now I got a dose range of 8. Or how about 100, 10, 1, and 0.1? Now I got 1,000-fold. All right. So the key is how low can you go? All right. So the whole thing is of how do you allocate the spacing between those doses, because we're dealing with just a few discrete doses. So can we set up all possible doses? No way. There's no way we can set up all possible doses. All right. Now we have only limited number of fixed doses. All right. So let's first look at the multi-center design. All right. So here's a multi-center design. I got placebo, low, medium, high. I got 3 doses plus placebo. And I got different centers. Now, center 1 is a fast recruiter. By the time we complete the study, we have sufficient patients in it. Center 3 is okay. You know, we still have a few patients in each treatment group. But center 2 is a slow recruiter. By the time we complete the study, they recruited only 3 patients. So we got a zero cell problem. Of course, when we have a zero cell problem, then the treatment by center interaction is not estimable. All right. So we can imagine the more doses you're going to have, the more likely you're going to have zero cell problem. All right. So multi-center design, and even though we're not paying much attention on multi-center design, we're not paying attention to like multi-regional design and things like that, still the same problem exists, right? The more doses you're including in the study, the more likely you're going to have zero cell problems. And of course, there's always formulation considerations. Right? Like I said, if you have 5 milligram tablets, good, you can do 5, 10, 15, 20, and so on and so forth. But you cannot do 7, you cannot do 3. All right. So there are limitations that practical limitations that the number of doses can be that can be tested. And of course, for any dose ranging design, we want to have a placebo, we want to have MTD in it. That already took 2 groups. Do you incorporate active control? Then that's already 3 groups. Okay. We're not going to spend much time on in titration designs, but just the number of doses can be tested are rather limited. Okay. Now, too few doses may not cover a wide range. All right. If you have only 3 doses, well, like I said, 160 and 20. All right, you can probably cover 5-fold dose range, right? But if you have 4 doses or 5 doses, it's more likely you can cover a wider range. Can we study all possible doses? No way. We can never study all possible doses. The true problem is under a fixed total sample size, too many doses left, very few subjects per dose. So what you're going to lose? You're going to lose precision. All right. Suppose I have a total of 300 patients. All right. For a total of 300 patients, if I'm doing a POC study, well, easy, 150 on MTD, 150 on placebo. We're done. We can do a POC, right? Now, if I have 2 doses plus placebo, in other words, high dose, low dose, and placebo, well, 100 patients in each group, right? Fine. Placebo, low, and high. We got 100 each. Now, if I had 3 doses, low, medium, high, plus placebo, then I got 75 per group. Now, if you want to incorporate a few more doses, say 4 doses plus placebo, fine. You still have 60 patients per group, right? And you can go to 5 doses. All right, you go to 5 doses plus placebo, you got 50 patients in each group. Well, that's reasonable. All right. So under fixed total sample size, too many doses left very few subjects per dose. We have done very intensive simulations. It is recommended to use 4 to 5 doses plus placebo. So beyond 5 doses, it became less practical. All right, you say I have a 7 dose study or 8 dose study. Then the blinding, the logistics, and all those kind of stuff, and the formulation, and the number of bottles of pills patients will take, that's going to be a lot more logistic headaches. But of course, 3 doses is not getting it. All right, so 4 to 5 doses is very appropriate. So what I tried to do back in the 90s was we try to come up with something that is very intuitive, that's not model dependent and stuff like that. Right. So what am I assuming here? I'm assuming 2 things. All right, two assumptions. I'm assuming MTD was guessed correctly. This is my MTD, and I'm assuming monotonic dose response relationship. Now I'm sitting down and design the next study. So if I'm allowed only 2 doses, all right, if I'm allowed only 2 doses, so it's very intuitive and very natural to say, if I call MTD being 1, placebo being 0, I call it this 0.5, all right, we just take a half. It's very intuitive to allocate 1 dose on, above 0.5, 1 dose below. I'm not saying it's exactly 25% or 75%. Of course, you can go up to here, you can go down to there or whatever. But if I have only 2 doses, there's really not much space you can play, right? 1 above 0.5, 1 below 0.5. All right, that's easy and simple, and people understand that. Now, what if you have 3 doses? So here's my recommendation. You keep the high dose as is, or whatever you did, even 75%, 80%, 90%, whatever you want to do. And then you take a quarter. So here's 0.5, that's MTD, that's placebo, 0. So let's call MTD being 1. This is 0.5, this is 0.25. So I keep my high dose as where it should be, and I further cut it to a 1 quarter, I allocate 1 dose below 1 quarter, 1 dose between 1 quarter and 1/2. All right, just keep going down this way. So I have 4 doses, I'll do this. Right, this is 0.5, this is 0.25, this is 0.125. Allocate the lowest dose here, the next dose between 0.125 and 0.25, the next dose between 0.25 and 0.5, and the high dose here. So I keep the higher doses as where it is and just keep going down to the lower end. Of course, when I take a cut, I don't have to just cut at 1/2. I can cut at 1/3, right? I can do 1/3, 1/9, 1/27, or whatever. All right. So I call this binary dose spacing BDS. All right. So binary dose spacing, the thinking is that for 2 test doses plus placebo, I'll keep 1 dose above 1/2, one dose below 1/2. And I continue this fashion to the lower end. All right. And any cut, I mean, I can take 1 over p as long as p is greater than or equal to 2. All right. I can take 1/2, which is 1 divided by 2, 1/3, 1 quarter, or 1 over 2.5, or anything like that. You can come up with different ways. But it's not a precise thing you have to do exactly, but it's just a general framework of thinking. All right. Now, the advantage of it is being non-parametric model independent. All right. And apply to titration design, sequential design, active control, early or late phase. I want to emphasize that model independent part. Okay. If you look at the drug development programs where they fail in finding the right range of doses, in most cases was because when the statistician designing the study, the statistician was assuming a model. And as we know, all models are wrong, some are useful. And I would say in dose ranging designs, models are pretty much useless. Okay. Now, the danger of using model is that you tend to believe that's the right model. And your design is based on that model. And in most cases, that model is wrong. That is a wrong model. Okay. Of course, later we got into MCP mod. They recommend many models. So as long as one model will catch it, you may have a good chance to do it. So that's fine. But why do you bother with so many models? All right. A model independent way of thinking, the best advantage of this binary dose spacing is easy to understand. All right. So when we say all models wrong, some are useful. Why some are useful? It's because the non-statisticians, they can understand. So then that becomes useful. That's the same thing with oncology studies, phase 1. Even though there's so many methodologies, we have 3+3, we have A plus B, we have EWOC, we have BLRM, we have CRM, but still mostly used phase 1 cancer trials are 3+3. Why? It's because it's easier to understand. So when you design a study, please not just think from a statistical way or from a mathematical way. Think about from the non-statistician way of thinking. So binary dose spacing become very useful. The reason it's useful is because it's simple and it's flexible. It's easy to understand. So I have two assumptions. The assumption is MTD is known and there's a monotonic dose-response relationship. And this proposal is very intuitive and with wide applications. Doesn't require any models. And this is just a general recommendation. It's not one size fits all because you already have preclinical information. You already have information about drugs of the same class from other companies, things like that. Please just go ahead and take advantage of it, right? But this binary dose spacing way of thinking is just providing a framework. And the most important part of the thinking is that you want to have a wide range. And the wide dose range came from the low dose it came from how low can you go. So that's the key. So I call this drug B. All right. Remember the previous drug I called it drug A? I think after about 10 years after drug A, I've been working on this dose ranging problems and came up with this binary dose spacing. Oh, by the way, the binary dose spacing paper was published in 2002. And I think I get the chance to design the study in 2004, 2005. But this is not what I designed. This is a previous study. So the previous study is completed. And the project transitioned to me. So the previous statistician designed a placebo 50-250 dose. And it's a 2-week study. And again, it's lower means better efficacy. So you look at placebo after 2 weeks and the 50 milligram and 250 milligram. Looks like we're having a drug. And I'm supposed to design the next study. Right? This is a secondary endpoint from that same study. All right. So I need to design the next study. All right. I have to look at what information do I have. I say the safety profile indicates the high dose could be too high. 250 could be too high, right? Actually, 50 and 250 are similar. You don't really have to go up to 250, okay? Secondary endpoints are used to help design the next study, use of MCP mod. So later we're going to introduce MCP mod. And I'm considering a linear model. So here's what I designed, all right? Now, when I saw the results from that first picture, my first question was, do you have a 2.5 milligram strength? Okay. They did. They have a 2.5 and they have 12.5. They have two sort of tablets, okay? Two strengths, all right? Length of study restricted by toxicity coverage. By the time I designed my study, I got 4-week tox coverage, so I get to design a 4-week study. So my next design is placebo-controlled. I use an active control also. All right. By the way, when we're running this study, this indication is very easy to recruit. So I can use many dose groups, and I can use a larger total sample size. And the whole study will turn out to be very cheap. It doesn't take a whole lot of investments. So I got placebo control, active control, and I proposed 5 test doses: 2.5, 5, 12.5, 25, and 75. All right. Let's think about the binary dose spacing way of thinking. All right. If I'm assuming MTD is 100, all right, although we tested 250, but apparently 250 is not doing a lot better than 50. So why don't I just stop at 100? So your high dose should be around 75. Well, that's reasonable. All right. And then this next dose is 25. Okay. Now, because we have two kind of dose strains, we got 2.5 and 12.5. So I can take advantage of 12.5. I can have 6 tablets here and 2 tablets here and 1 tablet here. So I got these 3 doses. From the binary dose spacing way of thinking, you're moving down from 75 down to 25 to 12.5. And now I got 2.5 strains. So I got 2.5 and 5. I mean, 5 being 2 of the 2.5. So this turned out to be the 5 doses I was proposing for this study. Again, like I said, we have placebo control, active control. So this whole study has 7 treatment groups, and here's the results. I want to say I'm very happy with these results. Okay, so you clearly see some kind of dose response, and the active control. Here's the active control. Your high dose and active control is comparable, right? Well, this is 5, this is 12.5, this is 25, this is 75. You see that? So here's placebo and 2.5. So from 5 onward, 5, 12.5, 25, and 75, there's some kind of dose response. Now, the best part of this design, is 2.5 doesn't work. Now, why is that good? Remember, in the previous lectures, I said minimum effect dose is mission impossible. It is almost impossible to find a minimum effect dose. But in the study results like this, people are going to say 5 is your minimum effect dose. Of course, you can argue, why don't you say 3 or 4? All right? It doesn't really matter. You don't have to go to 3 or 4. There's no need to split the hair. Right? You say 2.5 doesn't work, and 5 works. So people can accept 5 being the minimum effect dose. Now, this is very informative in the following sense. If you think of the previous study, we studied up to 250. So the MTD could be around 250 or even higher. Let's say the MTD is 250. 5 is 1/50th of MTD. Any drug regulatory agency is going to say 5 should be safe enough. All right. Now, even though you go up to 75, which is 15, you go to 75, which is 15 times of 5, it's still rather safe, and the response is better. All right. So when designing studies, many times the challenge being don't use low dose because low dose doesn't work. Actually, that's precisely the reason you want to use a low dose. So how do you find the minimum effect dose? It's not you come up with something that's well-defined minimum effect dose. There's no such a thing. But if your design has a wide enough range such that the low dose doesn't work, then you can establish some understanding about your minimum effect dose. All right. So these two drugs, drug A and drug B, tells us the importance of dose spacing. Okay. And what are endpoint? Are we measuring PD marker, clinical endpoints, safety endpoints? And we know efficacy cannot be observed from normal volunteer. So phase 1, you cannot study efficacy. All right. In early phase and late phase, your endpoints could be different. All right. How long do you follow after baseline? And how do you handle multiple endpoints? All these kind of stuff. So I'm going to skip a few slides, and I want to talk about combined POC and dose ranging design. Okay. Nowadays, in most companies, once they get into phase 2, they start with a multiple dose design. They call it phase 2, and that's sort of incorporating both POC and dose ranging. Remember, POC is very simple, high dose against placebo. Right? Now, if you have multiple doses in it, it doesn't mean you're not going to do POC, you're still going to do POC. All right. So for illustration purpose, we use 3 test doses. However, it's generally recommended to use 4 to 5 doses in dose finding study. All right. So 3 doses are going to have 4 parallel groups, low, medium, high, and placebo controlled. So you can use contrast to combine the information. All right. So what is a contrast? So let's look at these contrasts. So this contrast is high dose against placebo. That's easiest. You do a POC. You say, if high dose is different from placebo, then I have the drug works. Now, can you take advantage of the medium dose and low dose? Yes, we can do this. This is what we call OLCT, ordinal linear contrast test. All right, it's -3, -1, 1, and 3. Okay. Now, this gives us some kind, we call it ordinal linear. It's kind of linear, right? Because the spacing is the same, right? I mean, the response space. Placebo to low is 2, right? Low to medium is 2, medium to high is 2, all right? And then, of course, we have to talk about contrast. Contrast is that the if your coefficients add up to be 0, then you're talking about contrast. So we can design this contrast. We can say there's a ordinal linear relationship, or you can say the low dose does not work. Low dose and placebo is the same. And the medium dose, high dose works the same way. You can do it this way. We can say the low dose and medium dose doesn't work. Only high dose works. Or you can say the low dose, medium dose, and high dose all worked. All 3 doses worked, but placebo doesn't work. So you have these proposed sort of dose response relationship, right? So these are different contrasts you can do to test for your POC. So this is a contrast test setting, all right? So the null is that none of the doses works, or you can translate into a contrast like this, all right? So note that in this null, if you reject this null, all right, then this null will be rejected, okay? So if you reject this null, then this null will be rejected, all right? With the restriction that the coefficients has to be adding up to be 0, okay? So that's a contrast test hypothesis. And there are a lot of advantages of writing a contrast. It's a single degree freedom. You can just do a t-test and so on and so forth. So you can use the contrast test to calculate your sample size. That's how you calculate sample size. So for a given set of means of all treatment groups mu I and given allocation ratio F5 fraction, okay, for find contrast coefficients which maximize the power of the POC test. So you can do the optimal contrast independent of the total CI. All right. So only the values of response that selected those groups would impact the power. So here's an example. You look at different. Suppose we have equal allocation. All right, equal allocation. You look at now the black curve is this one. All right, 0, 0, 0, 1. All right. Then your contrast coefficients are like this. Or you have 0, 1, 1, 1. That's a red curve. You have the contrast coefficients like this. You can do like this, a step function, like the green one. Here are the coefficients. But if you have a different allocation ratio, all right. Now here we're allocating 1, 2, 3, 4, 5 treatment groups with the same sample size. But here you can do a 2 to 1 to 1 to 2, 2 to 1 to 1 to 1 to 2 allocation ratio, and your coefficients will change. And what we want to do is we want to propose this OLCT, ordinal linear contrast test. All right. So for OLCT, if only 2 doses, the coefficient is very simple. All right. Placebo and high dose. You don't have to give any weight to the low dose. You just want to do a POC. So that's very easy. So -1 plus 0 plus 1, you got a 0, right? So coefficients sum to be 0 and it's equal distance. Now, what I just showed you earlier was that -3, -1, 1, and 3. If you have 3 doses, 4 doses, -2, -1, 0, 1, 2. 5 doses, -5, -3, -1, 1, 3, 5. So these are the coefficients. So I don't have to calculate all those fancy coefficients. And so here's some simulation that we did. All right. Now, in this simulation, you have 5 dose response models, potential models, 1 being linear, and 2 being a step function, and 3 and 4 and 5, you know. 3 is kind of quadratic, right? So we have the 5 potential models, all right? The true dose response, the true underlying dose response being one of these 5 models. You look at the contrast. Remember, I showed you the proof of concept, right? High dose against placebo, or this linear contrast, or this only high dose works, or this one that low dose and placebo doesn't work, medium dose, high dose works, or all 3 doses work similarly. And you try to get the power. Power will be about 80 to 90%. You know, the pink color means any power below 70%, and red color being any power below 50%. Okay, so this is based on 1 to 1 to 1 to 1 ratio. And if you do a 2 to 1 to 1 to 2 ratio, you can see this kind of power. All right, so in both cases, we will say high dose against placebo is still very good. Why? Because if you're assuming monotonicity, of course high dose should be better than placebo, right? If the drug works, because we assume monotonicity. The higher you go, the better chance you can get. Now, OLCT is not bad, all right, compared to the high dose against placebo, all right? So, of course, I mean, this is my colleague, Kiki Deng, and we sort of work on this. We try to promote people use these OLCT method, right? And of course, we can do multiplicity adjusted parametric contrast test. So now a non-parametric contrast test. So in this is that people are moving into MCP mod. So in MCP mod kind of thinking, they're looking at the maximum T. In other words, they're going to have, they propose like 5 or 10 or 15 potential models, or 20 or 18 or whatever potential models. And they look at the highest t value. Remember, for each contrast, for each model, they write it as a contrast. And for each contrast test, you can do a t-test, and then you use a t-test, the maximum t value compared with a critical value. If you can see the maximum of that model, if that works, then you can say concept is proven. And of course, we can have a family of contrasts like this. You can have a Dunnes family, you can have a Williams family, you can have Marcus family. Okay, and then you sort of perform these kind of, so the MCP step is sort of looking at the multiple comparison adjustment for alpha control, because you look at the maximum T, you sort of control the alpha. So the basic idea of MCP mod is when you combine POC and dose ranging together, you use MCP to do the POC, and use the modeling to do the dose ranging as exploration or estimation. All right. So MC mod is an approach that the primary objective is to show the drug works. Secondary objective is to show the dose response relationship under one methodological umbrella. All right. So that's another example. And you can make some comparisons. Okay. What is the sample size of MCP mod, OLCT high dose against placebo, Dunnes, Williams, or Marcus? And you can do some sample size given the desired power. So MC mod does pretty well. You know, they have the smallest sample size requirement. And OLCT is sort of, you need a little higher sample size. High dose against placebo, you need an even bigger sample size. And these other methods, you need bigger sample size. So the performance of MCP mod is not bad, but it has to be on all the MCP mod candidate models, at least one of them was guessed correctly. Where OLCT, I don't have that requirement. You know, I have only two requirements: MTD estimate correctly, and the monotonic dose response relationship. So it's least amount of assumptions. So I talked to you earlier, right? When you try to design a study, you try to set up a low dose, and then the team will say lower dose doesn't work. All right, don't use a low dose since they're not going to work. Well, this is the main objective, phase 2, to find it out. All right. So I have a few more slides, but I don't think I want to take much more time on this slide set. So we can stop here. So that completes my presentation about phase 2 dose finding. Thank you.